This video is about simplifying complex Boolean expressions using the laws of Boolean algebra. It follows on from a video that explains how the various laws of Boolean algebra can be derived. Ideally, you should familiarise yourself with these laws first. Simplifying a Boolean expression minimises the number of logical operations involved. Because a Boolean expression represents a combination of logic gates, an equivalent expression with fewer operations represents an equivalent circuit, but with fewer gates. This video shows you how it's done. Application of De Morgan's theorem is covered in the next video. These are the laws of Boolean algebra. You're going to need them handy. Learning to apply these laws is a bit like learning to play chess. First, you need to learn the basic moves. Then, over time and with practice, you'll get better and better at combining sequences of moves in a game. Before seeing these laws in action, let's risk stating the obvious. These laws illustrate patterns of variables and operators that we'll be attempting to identify within complex expressions. For example, if we see the term d and 0 within a complex expression, then we can apply the Annulment Law and replace this term with 0 alone. If we see the term not C within an expression, this is an example of double negation, and the term can be replaced with just C. Let's also take a look at some useful interpretations of these laws before we see them in action. The Annulment Law states that any variable ANDed with 0 is 0. Think about it. Any number of different variables ANDed together with at least one 0 in the mix will also result in 0. This becomes clear when you examine this combination of AND gates. The Annulment Law also states that any variable ORed with a 1 is equal to 1. Indeed, any number of variables ORed together with a 1 will result in a 1. This set of OR gates makes it obvious. In fact, we can go even further and say that anything ORed with a 1 is a 1. So, for example, not A and B, or 1, is also equal to 1. We can also infer some variations of the Distributive Law. Suppose we identify this term within a complex expression. There are 4 variables, A, B, C and D, and 2 sets of brackets. But this is just a variation of the first part of the Distributive Law, the so-called OR Distributive Law. We can go ahead and expand this term by ANDing each variable in the first pair of brackets with each variable in the second pair. The 4 new terms we've generated are now ORed together. You may have come across an analogue of this method of expanding brackets in regular base 10 algebra. Some people call it the crab claw method. In regular algebra, it's properly known as binomial expansion. Here's a similar variation of the other part of the Distributive Law, the AND Distributive Law. When it comes to simplifying complex expressions, expanding brackets might seem like a backwards step, because it increases the number of operators in an expression, making it even more complex. But you'll soon see that expanding a term often creates opportunities to eliminate other terms. Just like playing chess, sometimes it's worth making a few sacrifices to advance your game. Performing the distributive process in the opposite direction is also very useful. Being able to identify and collect together common terms is called factorization. Spotting opportunities to factorize takes practice, but if you can spot them, factorization is a very useful technique indeed. Here's another variation of the OR Distributive Law. There are 2 sets of brackets again, but only 3 variables this time, A, B and C. We can expand these brackets in the same way, making sure that we AND each variable on the left with each variable on the right. Notice this time we've generated the term A and A, which can be reduced to just A using the idempotent law. Here's a similar variation of the AND counterpart of the law. You can see that this time the expansion generates A or A, which again equates to simply A. At first sight, this term doesn't look like a candidate for expansion using the distributive law. The pattern of and or operators is not the same as in all the other examples. Let's add some brackets for clarity. We can see that in every other example with two pairs of brackets, the operators within the brackets match, and the operator between the pairs of brackets is different from the operators inside the brackets. But if we think of the contents of the first pair of brackets here as a single variable, then the pattern of terms and operators now looks more like an example of the original or distributive law, and we can go ahead and expand this term. This particular interpretation of the distributive law is extremely useful and well worth keeping an eye out for. You'll see all of these variations in action soon. Let's put these laws to use. Here's an expression with one OR operation, one NOT operation, and one AND operation. This is the combination of logic gates that it represents. It has one OR gate, one NOT gate, and one AND gate, as you'd expect. Our objective is to simplify the expression, minimizing the number of operations involved. There's nothing obvious that can be eliminated immediately. So let's expand the brackets according to the distributive law and see where it takes us. Now we can see an opportunity to reduce the term A or not A to 1 by applying the complement law. The identity law states that anything ANDed with a 1 is itself, so 1 and A or B is A or B. This is about as simple as we can get with two variables. The brackets aren't needed here. So the original combination of logic gates can be replaced with a solitary OR gate. As a check, you can see that the truth table of the original combination is the same as that of an OR gate. But clearly, a single OR gate is much simpler. It needs fewer electronic components, so it's more reliable, it's faster, it generates less heat, and it's cheaper to make. Here's another example of an expression that we might be able to simplify. This is the circuit that matches the expression. The term A or not A jumps out at us. This can be reduced to 1 according to the complement law. Now we can see 1 or not B. The annulment law allows us to reduce this to 1 because anything ORed with a 1 is a 1. Finally, the identity law can be applied because anything ANDed with a 1 is itself. So these two expressions are equivalent. Examine the truth table for the original circuit and you can see that this is indeed the case. The output of the circuit is always the same as A. In other words, the original combination of gates is essentially useless. A simple connection from A to Z will do exactly the same job. Here's another example, and the circuit it represents. If there's no obvious place to begin, there's wisdom in adding a few extra brackets for the sake of clarity. It's really important not to change the meaning of the expression when doing this. Notice that terms that were ANDed together are still ANDed together. Now we can more easily see that part of the expression can be expanded using the distributive law. The combination of variables and operators highlighted doesn't immediately suggest that this is possible, but by treating the term B and C as a single variable, then we can AND it with B in the second term and we can AND it with C in the second term. Now brackets can be great for improving the clarity of an expression, but sometimes they can have the opposite effect. This is starting to look a bit too busy. So let's get rid of some of the unnecessary brackets this time. The meaning of this expression hasn't changed, but what we've done has revealed opportunities to use the idempotent law. Twice in fact. B and B becomes B, and C and C becomes C. Yet another opportunity to use the idempotent law has become apparent. If A or A is A, it follows that B and C or B and C is B and C. We're nearly finished. Our final move is to make use of the distributive law to factorise the expression by pulling B out of each term in brackets. So, these different combinations of logic gates do exactly the same job. Once again, one of them is much simpler, making it more efficient and more cost effective.